Welcome to Water Bounds of River Basins. My name is Andreas de Jong. In today's video, I'm going to show you how to delineate a catchment in QGIS. We're going to be working on the Mirani reservoir in western Balochistan, Pakistan, and I'm going to show you all the steps you need to take to derive the catchment from the SRTM90 digital elevation model. I hope you enjoy it. This is the Mirani reservoir in western Balochistan, Pakistan. We also have the associated drainage network of the dashed river basin and the SRTM90 digital elevation model. Today we're going to delineate the catchment area of the Mirani reservoir, but to do that we're going to have to reproject our DEM, which is currently in WGIS 84. So let's have a look at our project CRS. It is also in WGIS 84 geographic. What we're going to do is to reproject it to UTM zone 41 north, which is the correct one for this part of the world. As you can see, the purple rectangle is inside of our red area. Press OK. We've reprojected our project, but now we're also going to have to work on the DEM. The DEM is quite large, so the first thing I want to do is to cut a smaller piece out of it. So select the SRTM90, go to Raster, Extraction, Clip Raster by Extent, and the clipping extent, we'll look at the drop-down list and we're going to use Current Map Canvas Extent. Press Run and close. Okay, now we have a clipped raster. We can switch off the other one and we're going to reproject it to UTM zone 41 north. Go to Raster, Projections, Warp. The source CRS is WGIS 84 and our target is our project CRS, which is 41 north. Resampling method is very important. Let's use the bilinear one, and for the output file resolution we can use more or less the same size as the input DEM, which is 90 meters. Press Run. Okay, now we have our reprojected raster, and if you have a look at the sides, they seem to be a bit warped. So let's zoom in a bit more and we're going to cut out our final raster. Again, go to Raster, Extraction, Clip Raster by Extent, drop down, use the current canvas extent, and this time we're not going to save it to temporary file, we'll make it a permanent file. Save file, and I'm going to call it Save and Run. Let's zoom to the layer. Here's our digital elevation model. Now what we can do is get rid of the other temporary layers. Those are the ones with this little symbol here on the right. Remove layer, and also maybe copy the colors across from SRTM90. So we go to Styles, Copy Style, All Style Categories, select our new DEM, right click, Styles, Paste Style, All Style Categories. The first operation is complete. We have prepared our DEM for the next stage of the processing. I'd like to have a better feeling for the topography, so what we're going to do now is to duplicate our DEM. Let's rename it. Okay, so we're going to put a hillshade on top, double click on it, render type should be hillshade. We're going to use a set factor of 5. The blending mode should be multiply. We're going to use bilinear for resampling. It looks a bit dark. Let's change our brightness to 50. Not bad. The next thing which we're going to do is to burn, or rather carve, the rivers into the DEM. Select the SRTM42 north, go to Processing Toolbox, look for r.carve. Now, our elevation model is our digital elevation model. Our vector layer is the rivers. Please check that the two coordinate systems, or CRS, are exactly the same. Otherwise, you might have some trouble. The stream width, let's make it 100 meters and also exaggerate the depth by another 100 meters. No flat areas allowed. Let's save the file. Press Run. Okay, so what we have here are the adjusted stream points, so the streams which have been burnt into the digital elevation model. And we don't need the stream points, just remove them. But maybe what we should do is just to copy the stars across. And let's have a look at some of these rivers. So what we can see here is that our rivers have been burnt in the digital elevation model. This is very important so that later on our digital rivers are in the same place as our real rivers. This is especially important in flat areas where the DEM often produces strange effects. If there are depressions in our DEM with no outlet, we call them sinks, and they need to be filled so that our virtual water can run off the DEM and reach all the downstream parts of it. Now, to fill our DEM, we're going to use a command called r.fill. Go to Processing Toolbox and type r.fill. r.fill.dir, this is the one we want. Our digital elevation model is the burnt one. We're going to create a new DEM. Now, we don't need the problem areas or the flow direction grid, so let's press run. Okay, now we have a filled, hydrologically correct digital elevation model, which we can use for calculating the catchment of the Mirani reservoir. The next step is to develop the flow accumulation and the flow direction grid. Go to Processing Toolbox and look for r.watershed. Our input will be our filled DEM. We have to set the minimum size of the exterior watershed to the size of the pixels, 90 meters. Don't change any of the other parameters except enable single flow direction. And now we're going to save our flow accumulation grid. So that is the number of cells that drain through each cell, and our flow direction grid or drainage direction. We do not need any of the other outputs, so just unselect them and press run. Okay, so there are two layers here. This one is the flow direction grid, which shows us the direction of the flow at the surface of the digital elevation model. And the second one is the flow accumulation grid, which is basically the digital rivers. And you can see how we have all little tributaries and the big rivers flowing here into the Mirani reservoir. Okay, now we're ready to delineate the catchment area of the Mirani reservoir. Let's zoom in to the outlet of the reservoir. So what we're looking for is this black cells here, which have the highest amount of flow accumulation cells upstream. We're going to go to Processing Toolbox and use the r.water.outlet tool. The drainage direction raster is the flow direction grid, and the coordinates of the outlet point, just pressing these three buttons here. Go to the first black cell downstream of the reservoir, click once, press run, and close. There's a new raster called basin. Let's zoom to layer. And this is the catchment area of the Mirani reservoir. So the next thing which we're going to do is to convert our catchment raster into a polygon. Go to Processing Toolbar and look for r.to.vec, raster to vector. The feature type is an area. We're going to smooth the corners and press run. Okay, so here we have a temporary polygon of the catchment area. Let's have a look at the attribute table. I'm going to do some editing here. Let's delete some of these parameters which we don't need. Don't touch the fit, of course. And let's add a new one. It is a text. We'll give it 50 characters length. Let's also calculate the area. Go to the field calculator, create a new field. We're going to call it area underscore kilometer squared. The output field type should be a decimal number. Search for area, and the one we want is $area. Have a look at the numbers down here. This is square meters, so let's divide it by million so that we have it in square kilometers. Now there's lots of decimal places. The way to get rid of them is to look for format, and we have one here called format number. Just put a comma, and then let's say we want it to 2 decimal places, close brackets, and you see that it is correctly formatted. Press OK and stop editing. Save and close. Okay, let's save it to a permanent file. Export, save features as. We'll save it in a geo package. The CRS should be in geographic because we're going to use it on other applications as well. Press OK. Okay, let's remove it. And I think what we're going to do is go to symbology, and instead of simple fill, we'll use simple line. Let's make the stroke width a little bit bigger. Okay, so here is our catchment area. We also want to export it for later use as a shapefile and as a GeoJSON. So right click, export, save features as. Again, we're going to be careful that it is in geographic. Press OK. And now we're going to export it also as a GeoJSON. This is the one we want. Under 2 data, 6 GeoJSON, Mirani catchment GeoJSON, and OK. Okay, so we don't need these 2 here, but we're going to use them on other applications in a later video. Remove the layers. Well, that brings us to the end of this video. I do hope that you've enjoyed it. You might be asking yourself, why do we spend such a huge effort to develop catchment polygons? Well, there's a simple reason for this. We're going to use them as cookie cutters to download very interesting data from the internet on precipitation, evapotranspiration, temperature changes, land use changes, whatever. And that will help us to develop better water bounds of river basins and also better management of reservoirs downstream of our catchments. Thank you very much for watching the video, and see you on the next one.